have many measurable quantities, more than parameters, free parameters. So we overdetermine CKM, which is good, you know, that then we have a lot of tests. And the essential point is that you can measure, for example, if you choose to parameterize through a usual standard parameterization, you can from experiment to extract S12, S13, S23, and then only other parameter is delta 13, and that is has to be able to fix all sorts of parameters. Of course, it's nice to say this, but we know that we have hadrons, we don't have quarks. Therefore, there is a lot of QCD, lattice. There are people who just do lattice gauge theories that work very hard, huge computers and so on, to do the hadronic part. But in the end result is this beautiful plot. Unfortunately, it's beautiful because the standard model is doing extremely well. I always say, I mean, I hope that you agree, that the standard model has something very peculiar. It performs better than the propaganda. We are accustomed to a situation where propaganda is much above the accomplishment. The standard model somehow it does better than the expectation, you know. So, and also another contradiction that we want the standard model to break. Usually you want people, if you have a nice model, you don't want it to break. No, we want to break. And the reason it's easy to understand because we know that the standard model is not a full story. And therefore, in order to get a hint from experiment, you need somehow something where the standard model has to be modified, and maybe with that modification we'll understand better, you know. It's a situation in fundamental physics is very peculiar in these days, you know. So, I'm sorry, I should go ahead. I never know which direction I should go. Oh, I'm going down. I'm sorry. I'm really sorry for this. Okay. So, now the origin of CP violation I mentioned. We don't know if it comes from Yukawa couplings or from some vacuum phase. This is aesthetically is very beautiful because, you know, it's putting the breaking of CP at the same level as the breaking of gauge symmetry. This was one of the motivations of T.D. Lee in 1973. I will not give you more details about this model because, as T.D. Lee suggested, that model is already ruled out because too much flavor changing scalar currents, you know, the Higgs violate. But if you complement that, introducing that theory, a symmetry, a very simple one, it's a flavored, in the sense that flavors don't transform in the same way, flavored Z2 symmetry, the simplest group that you can have. And you can have a very interesting suppression of those dangerous currents, and therefore the model, strictly speaking, is still alive with predictions. But we have not published yet. In about 2 weeks, we'll have things. So this will be very interesting because it has it is a model that can be ruled out. That's a quality, you know, to have a model that can be ruled out by experiment. This particular one, and the reason is because in this model, you cannot have the Higgs too heavy. You know, it cannot be 100 TeV. You know, it has to be of order below 1 TeV. So even in the more high statistics LHC, you may be able to see some of those defects. So a caution is already mentioned that in order to be models with spontaneous CP violation should have natural mechanism to suppress. This is what I just said, flavor change and neutral currents. Then I described this invariant approach to CP violation, which I find it very beautiful, which is coming back to the old ideas of T.D. Lee and C.N. Yang, that you should define CP by the part of Lagrangian, of course, that respects CP, and construct the most general transformation. So if you do that, I'm sorry, keep going in the wrong direction. Okay, if you do that, then you can define a very general CP transformation and apply it to the Lagrangian, and you see that the CP invariance obliges this to be satisfied. You have to have a unitary matrix that can do that. Of course, it will be very difficult to try by constructing the unitary matrix. Fortunately, you can avoid that by just working on these equations. In particular, multiplying by its Hermitian conjugate, then you can get this relationship that now you have only one unitary matrix that has to do this. You get this minus sign here that is very interesting. CP is, it has to have a matrix that does that with a minus sign. If you multiply the equation by itself an odd number of times, you recuperate this minus, you keep, and then you can derive this expression, okay? Which is not satisfied, and therefore CP can be violated for 3 or more generations. In the case of 3, you get this incredible result. You see that the invariant knows about everything that we learned at a great effort, you know, that, for example, that CP in the standard model goes away when there is degeneracy of quarks and so on and so forth. These invariants are beautiful and they can be constructed for any theory, okay? Now, this let me not repeat because it's not worthwhile. I already explained that. I talked about that the standard model, just you add nu r, and immediately you have a solution to the smallness of neutrino masses through the seesaw. And okay, I don't have any more things to talk here. I mentioned about the freedom you have to change rephasing the neutrino fields and charged lepton fields, and therefore changing the mass matrix of neutrinos. They transform in this way. Okay, you can build, you can count phases. You can, for example, looking at in the weak base where charged leptons are diagonal, you can count the number of phases in the mass matrix of neutrinos. It will be, these are the initial phases, but then you can eliminate n phases by rephasing the charged leptons and the neutrinos, okay? So that you can eliminate, and in the end, you have 6 real parameters plus 3 phases, okay? So 6 plus 3 is 9. So, and I will tell in the next slide that 9 is actually more than what you can get in the lepton. So the leptonic sector is completely different from the quark sector. The quark sector you have overdetermination of CKM matrix. In the leptonic sector you have underdetermination. And it is a great challenge for any young person to think of how to get more information about the neutrino mass matrix, okay? Very difficult, of course. I already can skip this. Then the PMNS matrix is written usually in this way. Nice, because it means it's connection between the electron and the new one. These are mass eigenstates, and so you get this is nice notation. I mean, this is not necessary. Then I mentioned that you see, I told you from the beginning that VCKM, the argument of any element of VCKM has no meaning. The only thing that is meaningful in the quark sector, as far as arguments are concerned, is argument of a quartet, because the quartet is a rephasing invariance, okay? And the imaginary part of the quartet is equal. All the quartets have the same imaginary part. That's why you can talk about strength of CP violation in the standard model. Here, with the Majorana neutrinos, bilinears of this type are meaningful, like this with this. You can rephase the phase of the charged leptons because they cancel. But you cannot rephase the phases of neutrinos, and therefore this is meaningful, okay? In practical terms, this means that its orientation of the some of the triangles, its orientation has physical meaning. Contrary to what happens in the quark sector, where orientation has no meaning, you can rotate the triangle, you don't change physics. So I said that you can define 6 independent Majorana type phases. This is a possible choice. From these you can construct combinations that are Dirac type invariants, but the building blocks are these Majorana phases. And I said a surprise that from 3 by 3 unitarity you can show that full leptonic mixing matrix can be obtained from these 6 independent Majorana phases. Okay, it's a very curious thing. You may say, well, how can from angles to determine a right triangle? Don't forget that I'm assuming unitarity, so you cannot blow up the triangles. That will break unitarity. Unitarity is the one that is makes possible to build this. Okay. Now, as far as parameterization, you can use the same parameterization that was used in the quark sector, like this. This is so-called standard parameterization. There is another parameterization that is very special for treating double beta decay that was described in all detail by Professor Giunti. It is to eliminate the phase from here. You can do that by writing this that way. What happens is that you are keeping a phase here, which means that you are going to change the Majorana phases. Okay. Therefore, I see. Yes. Then I've talked about the Dirac and the Majorana triangles. These are the Dirac triangles are exactly like the quark sector, and the Majorana is very special because orientation is physically meaningful. So this is one example. I already talked about that. So this is also the area of the triangle that I talked about. For example, you saw the double beta decay written in terms of in a special parameterization of PMNS. Here I'm not using any special parameterization, just the angle, this rephasing invariant bilinears, you know. So you get something like that, okay? So it's really Majorana phases that appear here in the double beta decay, okay? Now, this is the parameterization that I was referring to. It's very convenient to put one parameterization where here there are no phases, because this MEE that again Professor Giunti explained in detail is just this. So it depends only on this phase alpha 1 and alpha 2 if you put in this parameterization. But as you know, as it was emphasized in this contribution to double beta decay, you may have cancellations, you know, and that makes life harder. Now I come back to the counting of parameters that we had already seen. These 6 real parameters, because these, and then the 3 phases in this mass method. So you have the 9, while how many physical quantities in mu can we obtain through feasible experiments, okay? You have the mass differences that were already measured, theta 1, 2, theta 2, 3. Theta 1, 3 was a very important angle, was the last one to be measured, because people thought, yes. This one? I'm sorry. The previous one, I see. Yes? No, in the hand, I had that. Yes. Yes, yes. No. Yes. Yes. No, but you see, let's be careful. It's not a standard model any longer. No, the standard model, we don't have this mixing, you don't have anything. Yeah, but but no, the experimental, what we have very strong limits, and that is another area where we could have new physics, you know, and this is a very important part of our future, you know, is mu e gamma. It would be fantastic, you know, mu e gamma if it could be measured. I remember I was my first postdoc when SIN, you know, long time ago, SIN in Switzerland showed some thing that was interpreted as mu e gamma. See, when I even wrote a paper about that, but then I realized because at that time people, you know, didn't know this, you know, archives were not working very well, didn't exist. We just exchanged preprints, and there was immediately a paper by Weinberg and Bjorkane with 2x doublets showing that mu e gamma can take place. But anyway, coming back to your question, some of these things have strong limits experimentally. It doesn't mean that they are not going to be seen in the future. You know, there is a tremendous effort in that direction. Oh yeah, I see. You could also, yes. Yes, absolutely, rare decays, yes. Oh, yeah, very rare. No, that's very hard to get more. Okay, so let me go. So this is what Glashow counted. He was very pessimistic in a certain sense because he counted 1, 2, 3, 4, 5, 6, 7. Because he is assuming that you will never be able to measure the absolute mass of the neutrinos. You know, but maybe it will be measured. Even if that happens, you get only 8 quantities. But parameters, it's 9. So it would be desirable to think of anything, you know, that could add to these measurements. Okay. Now, an attempt was done by Glashow by postulating, in a way, ad hoc way, texture zeros in mu, and then he has a lot of predictions, you know. But texture zeros are interesting because they could come from a symmetry. But if you don't have a symmetry, it's very arbitrary because they are not weak bases independent, you know. If you change bases, they disappear, you know. So it is not, I mean, it's interesting, but we alternative together, I mean, Yanagida spent 2 weeks in Lisbon and we wrote this paper where we postulate it's a trivial thing. In a way, determinant of mu equal to 0. One of the neutrino mass equal to 0, immediately you can then reconstruct the full neutrino matrix if one of the neutrinos, and that has not been ruled out experimentally, you know. One of the neutrinos could be massless. Now, you can do the same thing, you know, CPR weak basis invariance in the leptonic sector. This is very interesting because you will see non-trivial results obtained in a very elegant way, okay? You have here the masses of the charged thing, and this is the Majorana mass for the neutrinos. I don't care where it comes from. I'm always looking at only looking at the low energy, so it doesn't matter where it came. You know, it came from seesaw, but I can't forget to write that in the neutrinos, just effective matrix, okay, here. So, as I said, the CP transformation properties of various fields are dictated by the part of Lagrangian which conserves CP. So I have to do the same exercise as I did before. You see, this is the matrix that can mix the various generations. And then if I do the same thing, I'm not going to repeat because it's exactly for the Dirac type invariant, it's exactly the same thing that we did for the quarks. And you get this for Dirac type CP violation in leptonic sector, that the trace of h nu HL to the cube equal to 0. I was mentioning UE3 as being very important because at one point there were some theories, you know, with symmetries that predicted UE3 exactly equal to 0. That would be in a way bad because then we could not have oscillations, CP violation oscillation. So the discovery of UE3 different from 0 is beautiful. For those who like particle physics, who want the field to develop, it was a great achievement. And just to contrast the leptonic sector with the quark sector, the precision, if you look at the particle data, you know, group, the precision in UE3 is larger, that was just discovered, than VUB that we have been measuring for decades, okay? So it's because in VUB you have hadronic uncertainties and so on, okay? So that is the difference between leptons and quarks. So this is exactly the same thing that you obtained in the, and again, for you to understand why Dirac type CP violation disappears, because the imaginary of Q, if one of the elements of BCK of PMNS is equal to 0, you just go to that quartet that includes, and of course that quartet will be 0. And therefore, all quartets have imaginary part equal to 0. Therefore, you kill CP violation altogether. Now you may ask another question, which is a way academic question. You know, what about Majorana type CP violation? One thing that people already knew, you know, is that with Majorana neutrinos you can have CP violation even with 2 generations. Okay, and there was only one phase. Therefore, it would be nice to build an invariant that sees that phase, analogous to this trace of the commutator to the Q. Okay? That can be constructed. I will not do here. It's not trivial in the sense that you try many times. We tried a lot of times, and we get always that for invariants that for 2 generations immediately vanish. So it doesn't have any physics. Okay, but this particular one does not vanish. And if I calculate this, one can calculate it by going to the, for example, by going to the bases where the charged leptons are diagonal. Then it's easier to calculate this. And the mixing matrix is just a Cabibbo type matrix with a phase, you know. And then if you calculate, then you get everything M1, M2. This is an incredible result for the following reason. You see here sine 2 gamma. So it means that if gamma is pi over 2, naively people thought, oh, you get maximal CP violation in neutrino sector. Wrong. You know, you get 0 because, you know, this invariant, people, Lincoln Wolfenstein discovered it by his intuition that this was the case, that with gamma pi over 2 you don't have CP violation, but there were many people before that made a mistake. But you don't need to do to those complicated thinking. Just calculating this invariant tells you that that in order to have CP violation for 2 generations, that this is of course sensitive to Majorana type phases, and therefore, if you are a model builder and you want to know if in your model there will be Majorana phases, you have to calculate this. Okay. Okay. So now I will be talking now about violating unitarity. Okay. Now, if you want to violate unitarity and put even limits on violation and so on, you have to build a theory that is sensible where CP violation is violated. I remember, it has nothing to do with this, but I share with you, I remember a famous paper that at least I enjoyed very much reading the paper of Weinberg, where he says, what are the limits of violation of quantum mechanics? And then he immediately says, this is non-trivial, because in order to put a limit, some parameter that is less than something violating quantum mechanics, you have to build a theory that is more general than quantum mechanics, that contains quantum mechanics in some limit. And then you would be putting a limit. And he says, that theory does not exist. Maybe strings have that, but I don't know. Yeah. Anyway. Yeah, yeah. So anyway, so here it is very easy, okay, to build a theory that is sensible, that is normalizable, everything, and where violations of unitarity are there. But anyway, before going to specific theories, let me tell you some. Suppose that you have indeed more CKM matrices larger nodes, so there is violation of 3×3 unitarity, okay? Now you have here in the 3×3 sector, you have 9 moduli, of course, 4 rephasing invariant phases, only 4 because 5 of them can be eliminated by rephasing. So 4 rephasing invariant phases. So altogether you have here in this matrix 13 parameters. So what does the standard model tell you? Standard model relates, because it is unitary, relates these quantities in a non-trivial way. Of course, the trivial way is normalization, for example, you know. But there is also a relationship between phases and sides of the unitarity triangle. So, first of all, I have to choose 4 independent rephasing invariant phases. So I put beta and gamma. I don't talk about alpha because alpha is not independent. Alpha plus beta plus gamma is equal to pi, as I mentioned many times. So beta and gamma, there is this chi that is, for those experimentalists sometimes often called this beta S, has already been measured, and the LHCb is going to measure even more precisely, I think. Chi prime is very difficult to measure, very small, we know, in the standard model at least. So the standard model with regeneration predicts a series of exact relations among the 13 measurable quantities, okay? So what are these? Some of these relations are very interesting. You know, this is just a comment about alpha plus beta plus gamma. You can make a convention without loss of generality where the argument of these are, you know, 0 and this quarter will define chi prime and so on. So without loss of generality, you can write the arguments of this 3×3 matrix in this way, okay? And I put here chi, but really very often people call this beta S. Then these are the relations. They are derived in a very simple way, which will be an alternative way of testing the standard model rather than this unitarity triangle that people do, okay? And people who don't want to do complicated computer, fits and so on, you can check with your pocket calculator whether at the moment this is more or less satisfied or not. So VUB is related in this way with some beta, some beta. There are a series of them. Among those are especially interesting the violation of any of these exact relations signals the presence of new physics which may involve derivation of 3 by 3 unitarity or not. This looks contradictory, but it is not. The reason why this could be violated not because the triangle is not a triangle, it's not closed, but rather because there are new contributions, for example, to beta, Therefore, what you measure is not beta, but some kind of beta bar, okay? That is why I made that remark. Now, the presence of new physics contributes to BD-BD bar mixing, BSB bar mixing, affects the extraction of VTD, VTS from the data, okay? So that is, new physics can do that. Okay, one example, SUSY extension of standard model can contribute to that. Now, it is interesting, and there is also a very interesting formula to check the new contributions to BD-BD bar mixing. Q can be D or S for BD-BD bar mixing or BS bar mixing, and so I'm parameterized some new contribution like a factor R, a real factor, plus a phase. So the parameters, when RQ is equal to 1 and theta Q is equal to 0, you get the standard model. But you can get new physics contributed. So from these formulas that I wrote, you can derive, from this formula, for example, I can derive an extraction of theta D, the new physics, in the same way with theta S, okay? So you have the extraction, for example, I get tangent of theta D. All this is measurable, okay? All this is measurable. I put beta bar here because I mean to go and, because in this framework I'm assuming new physics, so there is new contribution to the measurement of beta, and therefore I call it beta bar. This is the interesting quantity because that's the one that experimentalists measure, okay? So you can see right away that you can, with these formulas, you can see immediately. At the moment, this is consistent with 0, But if you have more precision, maybe you will be lucky and discover new physics through these very precise measurements. Note that all these are measurable quantities. That most of them have already been measured, okay? Another one that is very interesting, which is not contained in the unitarity triangle, is sine of beta S. Sine of beta S is approximately to an excellent, it's a very small error, a order of 10 to the minus 3, 10 to the minus 4. This relationship should be satisfied. So this is very cleverly combination because VUS, VUD are very well measured, beta and gamma are measured, so this is another way of measuring. Of course, we know already, even in the standard parameterization, that VUS, that the sine of chi is of order lambda squared. So this is lambda, this is 1, so lambda squared. But what this formula gives you is the coefficient. What is the number in front of lambda squared? The standard model gives you exactly what is this number, okay? The same for another way of getting, which is also very interesting, is by the measuring of VTD or VTS. Again, those who know about this extraction, the error in VTD or VTS, is much less than the individual errors in VTD and VTS. This is because many of the hadronic uncertainties cancel in the ratio. Therefore, again, you have a beautiful relationship. So we are all waiting for more precision data from LHCb to be able to maybe discover new physics. So since we are considering experimental tests of 3 by 3 unitarity of this geometric, one should ask the following question. How much time do I have? About half an hour. Go ahead. Yes. Can one say, as I meant, self-consistent extension of standard model where deviation of 3 by 3 unitarity may occur? can these deviations be naturally small? Because they better be small and naturally, not by fine-tuning, okay? And the answer is, to both questions is yes, okay? You see, it looks again that I'm doing a contradictory statement, because you see that in the very beginning of gauge theories, Weinberg and Glashow wrote a beautiful paper that I advise any student to read. And those who have already read a long time ago, I think it's worthwhile reading again. This was the last paper that Weinberg and Glashow wrote together, and it's a masterpiece, you know. And they put their conditions to, when you build, this was the beginning of gauge theory, where people were building all sorts of crazy models, and Weinberg and Glashow put some kind of order in the house and said, okay, you should really obey to these rules, to that rule. But they wanted exactly flavor changing, zero flavor change in neutral currents, because there was only the scale, the only scale was V, you know, the back propagation value. But once you have two scales, like we know from Sigaud, you may have naturally small quantities, are not zero, but are naturally small, like violation of unitarity in PMNS. There are violations, but they are automatically small. So this is something similar, okay? This naturalness, the smallness is, again, very similar to what happens in Sigaud. So we shall consider extension of the standard model with vector-like isosinglet quarks. What means vector-like? Vector-like means that the left-handed part, the particular case that I'm considering, is a singlet, and the right-handed part also a singlet. Immediately you see a similarity with the right-handed neutrinos. Right-handed neutrinos has a peculiarity that can have a mass, bare mass, that is gauge invariant. These guys can also have a bare mass. Bare mass gauge invariant means it's not protected by the gauge symmetry, which means it could be large. How large, we don't know. That's the weakness of all this, is because we don't know how large. If it's super, super large, then you will never be able to see these guys, the same way that many of the things of neutrinos are not visible if the right-hand neutrino is 10 to the 10 or something like that. But in this case, we don't need to put very large. It could be a few TeV, you know. So 7 reasons, I'm now making a little bit of propaganda, 7 reasons to consider vector-like quarks. They provide a self-consistent framework with naturally small violation of 3×3 unitarity, lead to naturally small flavor change in neutral currents, as you will see, provide the simplest framework, and this is certainly true, simplest framework where you can have spontaneous CP violation, no problems with flavor change in neutral currents, because they are naturally suppressed, with the vacuum phase, just one phase in the vacuum, generating a non-trivial CKM phase, you know. Important requirement. There is an experimental, I already emphasized this many times, there is an experimental evidence of a complex VCKM, even if one allows for presence of new physics. Therefore, the theory has to be able to generate a theory with spontaneous CP violation. They provide also new physics contributions to BD by mixing and BS by mixing, which is good for the experimenters to believe that maybe new physics is there and we need just to be more careful. It took a long time to discover neutrinos, you know, yes.
How about the D0
Oh, absolutely, absolutely. Also, for that, the model that I'm going to consider seriously is only in the down, only the down type. But if you put an up type, you're absolutely right. If you put an up type, you have D0 bar mixing. Okay? Here, if you put just down type, you don't have. But if you up type quark, vector-like, you have you also have contributions to D0 bar mixing. Anyway, D0 bar mixing is a very important quantity. Okay, that is certainly true. Now is a completely different area. Provide a simple solution to the so-called strong CP problem. You know, as you know, Etoft had a brilliant contribution, many brilliant contributions. One of them was to solve U1 problem. But he solved that problem, but in a way he created the strong CP problem, because in framework we saw that actually there is a term that you could write in the Lagrangian F mu nu tilde. It's a total divergence, so people didn't consider much, but if you take into account special configurations like instantons and so on, you have to take that into account. And then experimentally, this is very dangerous, because the neutron dipole moment limits one parameter that I call theta bar that has to be less than 10 to minus 10. And in the standard model, this parameter could be over the 1. So really, that's why people talk strong CP problem. There was a brilliant solution by Peche and Quinn, but it leads to they didn't predict actions they themselves, but then I think it was Wilczek and Weinberg that showed that kind of solution, strong CP problem, it leads to actions, which is an interesting thing because they could be candidates for dark matter. But so far we have not seen actions, so you could say, is there any other solution? And the answer is yes, okay? This solution belongs to the class of solutions that were in a completely different context, like grand unification, that were considered by Barr and Nelson. But I will give you a very simple model where that solution exists, and at the same time, you can generate complex BSCG. You didn't tell me how much time. I'm sorry. I'm sorry. 15. Okay, I think we have time. So how do I do that? Also, provide a framework where there is a common origin of all CP violations. You know, CP violation in the quark sector, we already seen. CP violation leptonic sector, one that can be discovered in neutrino oscillations. And also CP violation needed to generate baryon symmetry of the universe through leptogenesis. This is an incredible thing, you know, because the standard model has all the ingredients to generate baryon symmetry, you know, like baryon number violation, CP violation, and so on. But the experts in baryogenesis agree by now that standard model cannot generate the correct asymmetry. One of the reasons is that CP is too small, you know, in the standard model. Second is that the Higgs is too heavy. So we need an alternative, and a very simple alternative is leptogenesis that was suggested by Yanagida and Fukushita. Unfortunately, it's very difficult to test leptogenesis. People try, and even now there are people building leptogenesis with where it is generated at TEF scale, and then you can. But these models usually are more complicated. Maybe nature chooses that. But the motivation to build those models with a low-scale leptogenesis is just that you try to make things that can be checked, okay? That is the main reason. But I will tell you then how all this comes about. Okay, I already mentioned here many times there is nothing strange in 3 by 3 by deviation of 3 by 3 unitarity. The PMNS matrix, the leptonic sector in the context of type 1 seesaw is not unitary, and therefore we are not doing anything funny, okay? So let me build this model. I'm adding just one vectorial quark, D0, for simplicity. I could add 3, or I could add ups and downs, okay? All this, or only up. There is freedom for that. And I will add 3 right-hander neutrinos and a neutral complex singlet, okay? Now, the whole CP violation comes from the phase of this complex singlet. It's difficult to believe, right, in this, because, you know, this tendency to eliminate phases, right? So how come this one single phase can generate CP violation everywhere? You will see that I'm not cheating. It's really true, you know. So the model, in order to solve also the strong CP problem, I introduce a Z4 symmetry under which the left-handed fields transform with this I here. But then the D0 goes to the new vector-like quark goes to minus D0, and this scalar singlet also goes to is odd under the Z4. Okay. As I mentioned, this Z4 symmetry is something ad hoc, but it's just to solve the strong CP problem. Now, I'm writing here the Higgs potential. Of course, it will have the terms of the standard model plus you will have terms that see phases. In the standard model, in the Lagrangian standard model, you don't see any, in the Lagrangian of the Higgs scalar sector, you don't see any phase. Only phi dagger phi, no phase. Phi dagger phi 2 square, no phase. Here you have phases can be seen here because as you have this term, this does not see, but this one is invariant, s square plus s square, and s to the 4th even you can build. So therefore, you can find a range of parameters where the minimum is in this value, okay? So if I write fully the Yukawa couplings, You see, these are the quark sector. It will have this form. You see, these are the three standard quarks. This is vector-like quark. They all mix, you know, after spontaneous symmetry breaking. And there is this zero here, 3 zeros. You know, this is a block of zeros. That block of zeros in order to solve the strong CP problem. I mentioned theta bar because that is one that is limited to 10 to the minus 10. Theta bar is equal to theta QCD. Theta QCD is the parameter that you write in the Lagrangian, okay? Because you don't have CP invariance, in principle you could write theta QCD. But in this theory, I'm imposing CP invariance, therefore I have the right to put theta QCD equal to 0. But then I have theta QFD, which is the argument of the determinant of the up quark mass and down quark mass. Okay? Now the up quark mass is real, you know, because I'm imposing CP invariance at Lagrangian level. So the determinant of M up is real, you know. Therefore, I don't have to worry about M up. But M down, the argument will be this one that is real multiplied by this one. But this one again is real because I impose CP invariance, you know, in this MD. You know, Gij, they are real. You know. So altogether, theta bar is equal to 0 at 3 level. Then you have to calculate high orders. Okay, I'm not saying that this is as safe as Peche Queen, but it's an interesting thing that you can get theta bar not too large in this way. And at one loop, you can manage things in such a way that are in agreement with the experiment. Okay, that is the solution. Let me now. So where are the phases? The phases are here. The only phase is this theta, but the Mj, they can have these terms. This is real, of course, but there is this phase that enters in an arbitrary way. So M1, M2, M3 are essentially 3 complex numbers, okay? These are large because they see that the vacuum potential value of S. This is also large, independent. The scale of this, in principle, this can be different from this, okay? Already anticipating the results. If you put M bar, very large, and this one's large but much smaller than this one, then all the effects go away, okay? And you don't have a generation of VCKM complex and all that. But most natural thing is to have only one large scale, which means that this one is of the same order as this one. And in that case, something very interesting happens. So you have a matrix like that, you know, I try to diagonalize, and then you can prove very easily, simple algebra, that effective 3 by 3 matrix, you know, that will dictate what is VCKM is the matrix that diagonalizes this, okay? I'm putting K minus 1 because it's not necessarily an Hermitian matrix, you know, the unitarity is not there, so, but you can always diagonalize. So you have this expression, okay? Here you have a real part. This is the so-called the down quark mass matrix in the basis where the up quark is diagonal. So you get a real matrix, but here you have a complex matrix because you have here M dagger is a column multiplied by a line, and these are phases, okay? So the very complicated phases here. Now you can see here if M bar is of the same order of magnitude as these, you know, you can see that this term is essentially of the same order as MD dagger. So the new physics does not decouple. You know, there are well-known exceptions to the so-called Appelquist-Carazon theorem. You know, this is one example where new physics in this type does not decouple, and therefore you can have. I'm sorry. You can generate the complex K that we want because of this term here. Another thing that could be, again, I'm speculating now, maybe the reason why we're not able up to now to understand quark flavor in the sense of the spectrum of quark masses and so on, because we are trying to always work with MD, you know, but maybe there is pollution. You know, there is pollution from new physics, from physics at high scale, because they contribute equally. So maybe most models, if not all, that attempt to understand the pattern of quark masses and mixings use just MD, you know, not this possibility of. So maybe it is possible to find some kind of regularity that will hint at a particular symmetry in frameworks where there are two conservations. But again, at this level, this is just speculation, okay? So this leads to natural small flavor Cheshire neutral currents because k dagger k is not equal to 1. It's not unitary, but they are very small. Deviations of unitarity, you know, k dagger k is equal to 1 minus s dagger s, but s is equal to, here there is a small, big suppression, small m, you know, over m. You know, this is m squared. So you see there is an order m over capital M. Very similar to what you have in seesaw. You have flavor change neutral current, but they are suppressed. So note that there is nothing saying about violation theory. I'm repeating the same thing because when I talked about this, very often people say, well, it's very strange violation. Some people who are not familiar with this say, this theory will never be able to be renormalizable. No, not at all. There is no problem over normalizability here. It's perfectly well defined. Now, I didn't talk about the leptonic sector, and maybe now 5 minutes. Yeah, I have time. Okay, in the leptonic sector, I can do the same because I promised that this phase will lead to everything, including CP violation needed for leptogenesis. How do I arrive to that? Here you have the full Lagrangian. These are masses similar to what I wrote before. I can go quick here. Again, you will have something, this is the seesaw, just the formula of seesaw. So the matrix K is the matrix that diagonalizes this. But the M is a generic complex matrix, so M effective is also a generic complex. K are 3 complex phases, one Dirac type, 2 Majorana type in K. And now I come back to the question of generating the baryon symmetry, right? Reminding you that ingredients for baryon symmetry of the universe generation is baryon number violation, C and CP violation, departure from terminal equilibrium. So what is the scheme that Yanagida and Fujita invented? Is that I can say in words, is that first create through the decay of right-handed neutrinos, a lepton symmetry. And that is created maybe at very high energies. In the simplest framework, it has to be at 10 to the 9 J. But there are other alternatives, okay, that put it much lower. And then that asymmetry, leptonic asymmetry, is transformed into baryon symmetry through Sphaleron, some non-perturbative at the electroweak scale, and then you create a baryon symmetry. All this is just words, but people calculate it very carefully. There are specialists, people do very carefully all these calculations. But the calculations are simple, and not very complicated. I mean, yeah, there are not many ambiguities, you know. So it is amazing that we can have a model to calculate the amount of matter in the universe, you know, a model from first principles, okay? It is an incredible thing. Why CP violation? I said that the standard model cannot generate sufficient bow. One argument that people give is that you say you have this trace of the commutator to the cube. You see, you have here mass to the 12th. You know, this is 224 to the cube, so it's mass to the 12th. And you have to put a dimensionless quantity. The natural thing is to put here the scale of electroweak transition. Therefore, if you do the calculation, just because quarks are very light, essentially, you get 10 to the minus 20, which is much too small to create a baryon asymmetry of the order of 10 to the minus 10, okay? Another reason is that the success of baryogenesis requires a strongly first order phase transition, which would require a light Higgs mass. In the beginning, this was satisfied, but then we saw that it was heavier, and then again, the standard model by itself cannot generate. So you can say, you can say that the existence of a universe with matter, you know, it is an evidence for physics beyond the standard model. This is not propaganda, it's really true. Yes. Oh, yes. This is in the standard model, only neutron Higgs. Oh, you are right. There are solutions for baryogenesis without leptogenesis, just regular baryogenesis in frameworks with more than one Higgs doublet. Yes, there are models like that. They are complicated, but yes, indeed, if you have more, this argument does not apply. This applies just for the standard model. But that will be new physics, you know. The type of new physics I personally like very much, the idea that there is more than one Higgs doublet. Why should it be nature that in the Higgs sector not have this a little bit of repetition, you know, which we don't understand, but it's likely that scalars also get repeated, you know. So now, so one concludes that the explanation of observed Bow requires a new physics to be understood. The model leptogenesis suggests for cogite, and it's possible. How does it appear here? I will do a little bit quick now. I don't have much time, but you write again the Lagrangian, and you have to be worried about diagonalization. Again, you get the 6 by 6 matrix, very similar to what we did before with vector-like works. And again, you get here the seesaw formula that I wrote, but the important thing is the counting of parameters, okay? Now we have to be very careful, because now you can go to a basis where the charged leptons are diagonal, and also the right-handed heavy Majorana neutrinos are also diagonal. So all the mixing is dictated by Dirac mass matrix of neutrinos, okay? This is complex matrix. So the complex matrix will have the, you know, many parameters. So counting the total number of parameters, the charged leptons is 3. Right-handed neutrinos are diagonal in this basis, you know, are 3. Then real parameters in YD. YD is a matrix, 3 by 3 matrix, so 9 phases, but 3 of them can be eliminated, so you get real parameters in YD. So these phases are going to generate everything, you know, because in the seesaw, all the phases are now in the neutrino mass matrix, you know. So the symmetry in the leptonic sector are just calculated in this way. And if you do this calculation, you can show that this is proportional to imaginary part of MD dagger MD. There is a very clever way of parameterizing this matrix MD in this way. They built in, you knew is the PMNS matrix. This is square root of the diagonal matrix of the light neutrinos, square root of the diagonal matrix of the heavy neutrinos. R is a complex 3 by 3 matrix, okay? So it means that the physics at low energies does not depend on this R. R disappears in the seesaw formula, R disappears, okay? So, but it's very important for MDMM that it appears, you know, in the leptogenesis, this R dagger R, okay? And therefore you see that, I mean, one has to be honest, you know, one cannot cheat in telling experimentalists more than what, you know, in this type of simple seesaw and simplest leptogenesis framework, there is no relationship between CP violation that is measured in the neutrino oscillations and the CP violation that is needed in order to generate these asymmetries, okay? But there are models where people introduce extra symmetries and so on, and assume a more complicated way of calculating this. This is so-called unflavored leptogenesis. You get, this is the simplest possibility. You cannot. If you introduce symmetries, it is possible to have a relationship. See, it is an incredible thing. You know, there is a paper where Glashow tried not only calculate the lepton, Glashow and Yanagida, amount of symmetry, but tell what is the sign. Because if you look the sign of the leptonic asymmetry, you not only can predict the amount of matter, but that it was matter that is produced and not antimatter in excess, you know, because the two things can be related in some frameworks. But in general, you don't get it, the relationship. So I think you can also build, I told you that you can always build invariants. You can build invariants that are sensitive to phases relevant for leptogenesis. This is what I wrote here. So conclusion is the origin of CP violation continues being an open and fundamental question. I'm sorry, fundamental question. From experiment, we know that BCKM is complex, but what is the origin, we don't know. There's possibilities that rise at the Lagrangian level from complex Yukawa coupling, or it is spontaneously broken by the vacuum. Neutrino oscillations provide a clear evidence for physics beyond the standard model, and we discovered that UE3 different from 0 opens up the exciting possibility of detecting leptonic Dirac type CP violation. As you know, this is one of the aims of many experiments, including Dune, you know, that they want to discover, which is collaboration between many institutions, including the US Fermi Lab, and CERN is also there, and so on. Leptogenesis is an attractive framework to generate baryon symmetry, which can occur even in the framework of a standard model with a right-hand neutrino. Difficult to test experimentally. That is very true. It is urgent to conceive feasible experiments which can measure physical quantities in mu beyond the 7 quantities mentioned by Gresham et al. Okay? Difficult, but what looks impossible today may be possible tomorrow. Okay? I mean, this we always should believe in the ingenuity of smart physicists, theoreticians, and experimentalists to build some way of measuring things. It would be very nice if some years from now we have a workshop with the title Leptonic Unitary Triangle Fit, because there is no such a, there was never a workshop with that title, but you may ask why. The quark, there are not hundreds, maybe tens of workshops with that title for the quark sector. For the leptonic sector, the reason is because there's not enough data, not enough data. Okay, I think that's all. Yes. It is more general. It is. This is simpler, but it's more general. And in that framework, you can have, yes, you're absolutely right. It's just more difficult to explain. It's a rather, complicated. If you want to explain well, I would have to explain all the details of leptogenesis. Like here, I just wanted to give a flavor of how CP variation, these models, can give the phases that are necessary for leptogenesis. But I agree with you that in so-called flavored leptogenesis, you could have even the matrix that you determine, PMNS could have a relationship with the size of baryon symmetry. Yes, but in this case, not. Yes. I'm sorry. Yes. Loud. Yes. I'm sorry, what is being big or small?
Big or small CP violation?
Yeah, a good question. It's not, I mean, it depends how you want. CP violation is measured by the imaginary part of this quartet, and in all quartets of the standard model have the same size. So it's a dimensionless number. So small means much less than 1. In the standard model, it will be like 10 to the minus 5. That the experiment tells us that. And it's not, but you should not associate that. So it means that phase of CP variation is very small. No, which phase, because the phase could be in the quartet, that's more important one, could be of order 1. It's this angle gamma. This angle gamma could be of order 1, close to pi over 2. But it is small because of mixing. Because in order to have CP violation, you have to have these mixings. Otherwise, you don't have CP. That is the thing. Okay, Martha.
Okay, so yeah, so today is my last lecture, and so I will cover the the issue of nonlinear completion of the theory I discussed so far. And I stress that there is an S because I will discuss several completions. So far, I at least in the second part, in the second lecture, I discussed the theory for just spin 2, right, h mu nu, propagating on some g mu nu. And as far as I discussed so far, those two objects are completely unrelated, right? And they are a priori different, right? Or could be different. So you can even argue, terminologically speaking, that to call that a graviton, because we know gravity is a nonlinear theory. And so there is a wish to, of course, non-linearly complete this theory of a linearly propagating h mu nu over an h g mu nu. Not only a wish, but also we know, of course, that we should do that because we have proved that gravity behaves non-linearly at various places, even in the solar system. Okay, so so obviously, we also want to find a nonlinear completion which in some limits is close to general relativity because we know general relativity is working very well. So a starting point is to consider, of course, the Einstein-Hilbert action, say for a metric G. And then imagine expanding this Einstein-Hilbert action around some background, which will give at quadratic order the kinetic term for h mu nu. But then we want to add a mass term. Right, to make this metric G now massive. So a mass term should be some non-derivative term, some terms containing no derivative of G, and we don't have much choice. The only thing we can make, right, of this type is basically a cosmological constant, so it doesn't work, right? So this cosmological constant, if we add a cosmological constant to this theory, it will not give a mass to the graviton. So one should do something else, and so the simplest possibility to make the graviton massive is to introduce now two metrics. So there would be one metric g mu nu, which will be the dynamical metric, that we want to make massive, and we can introduce another metric, f mu nu, which will be some background metric, which to begin with can be taken non-dynamical. So this metric is sometimes called the reference metric. And it can be made later dynamical. Then you have a theory with two dynamical metrics. But in what I'm going to discuss today, I will take the simplest point of view somehow, that this metric is non-dynamical. And then one needs, if one wants to make this dynamical metric massive, one needs to couple those two metrics together in some way. So we add to this Einstein-Hilbert action, we add an interaction term, which can be taken of this form. So there is some initial factor appropriate for dimension, say. And then one can show that under a hypothesis that I'm going to explain, this interaction term has to be of this form. So it has to be a function of a scalar function of g minus 1 f. So this is meant to be, g mu nu f nu sigma. So the tensor obtained by making the matrix products of g minus 1 and f, say. Okay. So this theory will have a Diffeo invariance, but it will be a Diffeo invariance just when you transform all the tensors at the same time, right? So meaning that you can make a DFO transform on the, say, metric G. And you have to transform at the same time the metric F. So I will use this transformation later on, so let me give them a name. So this will be 317, and this interaction term will be 311. Okay, so, right. That's a scalar function, yeah. Scalar function. It's a scalar, yeah, it's a function of a matrix in general, yeah. Although, I can also have in this function, I can take the trace of this matrix, and it will be then a scalar, right? A scalar function of scalar. Okay, so okay, so then I demand, I further ask that several things on this theory. I want that the theory, well, is invariant under this DFO, which are written on the blackboard here. Then I demand also that that I have, and this is not maybe necessary, but let's assume so, that I have a trivial vacuum, which is just flat spacetime, as a solution. So, meaning if I take f mu nu to be eta mu nu, I want that g mu nu equal eta mu nu is also a solution. So you see at this point, f mu nu is unspecified. It is some extra Neos specified geometry. And I'm just demanding that if I take this geometry to be Minkowski, then G is also Minkowski, say in the same coordinate system. So this is maybe not necessary, and I can relax this. And also, I demand that when I have this vacuum, I can expand the theory around this vacuum. So if I take this vacuum, so f mu nu is non-dynamical, so it's unchanged, but g mu nu, I can expand it around the vacuum above. And I demand that if I expand this theory at quadratic order into H, I should get back a Fierz-Pauli theory, right? So and this hypothesis have been used to define a special class of this type of theories, which were called sometimes the Pauli-Fierz universality class. This is a terminology due to a paper of Damour and Kogan in 2002, where they studied some aspect of this type of theory. Kogan, sorry, 2002. And I will call myself this theory non-linear Fierz-Pauli when they obey this hypothesis here. Okay, so in fact, you can make infinitely many examples of such theories, which obey these three conditions. And I'm going to give here maybe 3 examples of them, which were and which are important for practical and also historical reasons. So the first example of such interaction term is the following. You take such a term, you take, say, d4x, square root of minus f. So here, in fact, here I put a minus g, but you can absorb this into redefining your v function. Then you take h mu nu, h rho sigma, and I'm going to explain what are these big h. F mu sigma, f nu tau, minus f mu nu, f sigma tau. Okay, so h, this big H, so this will be equation 312, and this theory has been considered in a, sorry, tau is, yeah, tau is rho, yeah, absolutely, sorry. Sigma, why do I go? Sigma tau. Yeah, this has been considered in a paper of Boulware and Desert in 1972, which played an important role in this field. And h mu nu here is just the basically the difference between the two metrics. And so this is also an equation which I would like to remember. So you see, in fact, this theory is somehow reproducing the Fierz-Pauli structure of the mass term, but in a non-linear way now, because I have two metrics in the game, right, here. So it's fully diffo invariant, etc. I can do the same trick, the same type of, I mean, you can obtain a similar action, just changing, for example, here, F to G, and here similarly, right? G sigma nu tau minus G mu G sigma tau. And so this theory has been considered in another paper, also influential by Arkani Ahmed, Georgi and Schwartz in 2003. Since this is complicated to write with this big chalk, I don't write the name of the other guys. Okay. And this will be also, this will be a theory 3, 1, 2. No, 3, 1, 3. Yes. Okay. And so a last theory is in this family I would like to present here. Is more recent and somehow more interesting. Is so-called DRGT theories. DRGT theory. So standing for Durham, Gabadadze Tolle. In the year 2010, 2011, and they have the following interaction term. So the interaction term is, say, I could have put a minus 1 over 8 like previously here, d for x square root of minus g, and then it's a several parameter family of theory. So in fact there is 3 non-trivial parameters. So here I will put 4, but I will explain. So beta k are these parameters, so which are dimensionless. And then there is a function of some weird object, which is a matrix square root, the matrix square root of G minus 1f. So this is a matrix square root. So in fact, you can question the existence, etc., of the square root. This is quite interesting, but I will not discuss this here because I don't have time at all. But I will just assume this exists, and it does exist in generic cases. I wanted to mention that later on. Let me just finish presenting this because I didn't tell you what are these function E, right? This function E. So E naught is just 1. So basically, you see that beta naught parameter is just parameterizing a cosmological constant. So that's why I'm saying there is in fact 3 non-trivial dimensionless parameter here. But in fact, you can always, if you decide what is the mass of the graviton, you can set one of these parameters to 1. So you have left with a 2-parameter family of dimensionless parameter. Okay, so E1 of x, where x is a matrix, is just x. And then E2 of x is 1/2 of the trace of x square minus the trace of x square. Right? And E3 of x would be 1/3 of the trace of x cube minus 3 times the trace of x times the trace of x square plus 2 times the trace of x cube. So these are also called the symmetric elementary function of the matrix X, and they have a simple, you can write them as a anti-symmetrized product of 1, 2, or 3 x's here. Yeah, sorry. Yes, trace of X, absolutely. Sorry. Yeah, sure, yes. These are scalar functions, so, okay, sorry about that, yes. Yes, so in fact, so this theory was first discussed by these guys when F is flat, but it was then it was later extended somehow, and also some interesting results were proven by Hassan and Rosen in 2011 as well, or maybe 12, to the case 12, yeah, to the case of an arbitrary F here. So this is the same theory as Hassan-Rosen theory. Okay, but it was really discovered first by Durham, Gabadadze, Tolle. Okay, what time do I have? Yeah. Okay, so in fact, these kind of theories, all these theories within this interaction term, they also fall in the class of theories which were studied in the 70s, late 70s, by Salam and company, Strasdy and company, in the framework of strong interaction. They were so-called bimetric theory or FG strong gravity. And this is theory of this type, basically with several metrics, with two metrics, and however with different motivation. Okay. So now let me discuss some properties of these theories. So obviously the field equations, that is to say the one of the dynamical metric G. So if I add the possibility to have a cosmological constant, they have the following form. So there is possibly an energy momentum tensor due to the coupling of G to matter that usually is assumed to be the minimal coupling because you want to recover general relativity and equivalence principle, etc. And then you have a term which comes from the interaction term. This comes from the interaction term, S interaction, the F and G. So this is a variation of the interaction term with respect to G, right? And so this involves F and G, in general, and only F and G. Okay. So you see also that there is an interesting way to derive an equation out of this equation, which by taking just a covariant derivative with respect to G, because you have Bianchi identity here, which kills this. If I act with a nabla mu on that equation, right, and it will also kill this guy. So I will be left with an equation which is d mu of t mu nu G should be 0, right? And so this is a consequence of the field equation, but when you try to solve this field equation, it has usually interesting consequences to look at this equation. Okay, now I'm going indeed to discuss the some solution of this field equation in the framework of spherical symmetry. And this is a way to introduce the so-called Weinstein mechanism, which plays a very important role in this framework. So it was introduced by Arkady Weinstein in 1972. And in fact, as pointed out later in one of the papers of Damour and Kogan wrote several papers on these theories in the beginning of the 2000, in the year 2000, maybe 3 or something. And they pointed out that Weinstein, in fact, in his paper of 1972, where he discovered what is now called the Weinstein mechanism, in fact, did not really consider a theory of this type with an action, because the theory he considered didn't have an action, in fact, as proven by Damour and Kogan. But for what I'm going to say, it doesn't matter. and this is irrelevant. Okay, so the idea is to look at the spherically symmetric and static solution in this theory for obvious reasons, right? Solution of the field equation above here. So to do that, you do the usual stuff. You start, say, with a non-that, which is appropriate for staticity and spherical symmetry. And so here I can take the following on that. We'll put some big X here. For G metric, so I take the following on that, G of R dt square plus K of R dr square plus L of R square d omega square, where this is a canonical metric of the two spheres. And then for the flat metric, I can also put myself in a coordinate system where it is, obvious. I mean, I take spherical coordinates. So in fact, you can, if you maybe you can spot that it's not the most general on that you can imagine, even for staticity and spherical symmetry, because here you have only a common diffeomorphism. So there is no reason for which you could not have a dtdr term here. So usually you can eliminate this dtdr term by doing a field, by doing a diffeo transform, but then it will reappear in the other metric, right? So here there is an extra assumption that is both metric are commonly diagonal. But it does not play a very important role for what I'm saying, and this is where, in fact, usually the Weinstein mechanism is discussed. So here I have three unknown functions, which are J, K, and L, right? So I can, however, in order to compare this ansatz to this possible solution I'm going to show to a Schwarzschild solution, it's more convenient to change coordinate, to put only two unknown functions in the G metric and one unknown function in the F metric. So with this new coordinate system, here is how the metric reads. This is E nu of R, say, dt square plus e to the lambda of R dr square plus R square d omega 2. And then I have F metric, which is still the Minkowski metric, but in disguise, because it will contain an ugly term, 1 minus R mu prime of R over 2 e to the minus mu of R dr square plus mu of R square d omega square. And then I have my three functions are now the lambda, mu, and nu, right? So then what Weinstein did is that he tried to solve the equation of motion above here, which I'm going to erase. So he plugged into this Einstein, into this equation, this and that, say, and solve, try to solve. Okay, so the solution is not known analytically, but he tried to get it at the time, and still today we do that, say, by power series expansion. So we power expand the unknown function. So we write lambda is lambda naught plus lambda 1 plus lambda 2, etc. New similar expansion. Mu. And we just assume that lambda I, mu, nu I, and mu I are given by some small parameter, are proportional to the small parameter to the power I, or maybe I plus 1. No, that's really like that. So this also are function of R, yes. But they will be all, proportional to some small parameter with the same power. And eventually, we want this epsilon, basically, this small parameter, to be proportional to the Newton constant, to the power, to the Newton constant. Right? So we make an expansion. The idea is to make an expansion into the Newton constant, basically. So I mean, corrected, of course, by appropriate dimensional full parameter to make this expansion dimensionless, right? So what Weinstein, found is the following. Well, in fact, the first part is not really new to Weinstein. The first part is the order 0 in I, which is order 1 in the Newton constant. So when you expand at order 0, you find the following thing. So you find that mu naught is minus some constant over R. Lambda naught is the same constant divided by 2R. And mu is 1 over mr square, this constant divided by 2R. Mu naught. Okay, so this constant is an integration constant, and eventually, if you even do that in general relativity, what you say is that you match, say, this integration constant to large distance behavior, so that this constant will be given, will be proportional to the Newton constant or to the Schwarzschild radius. So, using this expansion, you discover that it does not match general relativity, right? Because general relativity would be, if you do such an expansion in the Schwarzschild solution, you would have the same coefficient here. I mean, this C would be equal to this C over 2, right? If you expand Schwarzschild solution. So this is not the case here. You have 1/2 versus 1 here, right? And so this is, of course, in fact, a consequence, another manifestation of the Van Damme-Vellman-Sakharov discontinuity. And this is why also you can say this theory has wrong light bending. Because in general relativity, you find the correct light bending precisely because if you have 1 here, you also have 1 and not 2, right? So this is not surprising. Okay? And so what you can do, however, as I said, you can, say, renormalize, I mean, the Newton constant, say to have a correct scaling with the force, the Newtonian force. So let's do that and replace this constant by some basically Schwarzschild radius. So there you still have a wrong light bending, say, but maybe you have a correct Newtonian force. And then, so that's not new, right? That's not new at all. Then what Weinstein did is that he computed for the first time, and this is really where the new thing happened, he computed the next order term. So this is order 0 here. And at order 1, what he found is the following. So for nu, there is, so it's order 2, so I mean, or 1 in I, so it will be proportional to g to the power 2. So this is a Schwarzschild radius, so there is a g right here. And so he found the following term here. And this is multiplied by some pure number. So this is some number which depends on the detail of the theory, divided by mr to the power 4. And then there is the next order would be proportional to rs cube. Okay. Then here there is a similar term, r square times some again number divided by mr4 plus similarly here an order rs cube. And here there is also rs bar square over r square times some number divided by mr to the power 6. So this is order 1, and this is now similarly order 2. Okay, so this was computed for the first time by Weinstein in, again, some theory which looks like the one I presented. And so what is interesting here is that you see various things. First of all, you see that this term, obviously, they are very well very badly behaved when m is sent to 0, right? They are diverging when m is sent to 0. And in fact, you can compute when this expansion is breaking down, when you let m goes to 0. This is rather easy. You just have to compare, say, the order 1 and the order 0. So rs over r square times 1 over mr to the 4 divided by rs over r. And so you see that this stays much smaller than 1 if and only if r is much larger than a scale which is called the Weinstein radius, which is rs m to the power minus 1/4 to the power 1/5. So the expansion is okay only if you are at larger distance than this distance that is called the Weinstein radius. Okay, so the point is that this Weinstein radius, if you want to put number in it, it is very large, very, very large, in fact, because you see the idea is if one wants to have some maybe interesting modification for cosmology, we should let m minus 1 to be Hubble size, right? And rs for the sun, we know it's 3 kilometers. So you can compute easily that this, in this case, it is 10 to the 6 light year. So it means that, for example, that you cannot conclude anything from the argument about light bending if you use this theory in the solar system, because simply the linear expansion is breaking down well at distances larger than the solar system, right? Okay, so now Weinstein did something. So okay, so he concluded then that this argument about Van Dam and Sakharov discontinuity killing massive gravity is incorrect. He did something further. He computed another expansion. So the idea, the question is obviously is what if you start from very far away and go towards the Weinstein radius. The question is what's going on when you cross the Weinstein radius, right? And so you had a question, Robert? Sorry. Okay. Yeah. So what Weinstein did somehow is, well, what he did is that he did another expansion of the solution. So he postulated, and I stress that it is a postulate. It was a postulate that at lowest order in this new expansion, you find the Schwarzschild solution. And then he computed the next order term. So maybe I'm not going to give the solution for mu because I will be out of time, I think, otherwise. But and it doesn't matter so much, although it has some interesting aspects. But let me just give the solution for nu and lambda, which are the one really an observer will measure, right? If it couples to the G metric. So he postulated that you have at first order the Schwarzschild solution, and then he computed the next order term. And the next order term, so there is as well some order 1 number here which depend on the theory, this big L1 and big Ln1. But what is interesting is that now you see the first order term are well behaved when the mass of the graviton goes to 0 now. And so you have here an order M4 term. And so the idea of Weinstein was, as you can see here, was to make an expansion in the mass of the graviton square because you can consider the mass of the graviton now as being a perturbation of Einstein-Hilbert action, and then you expand everything into this mass of the graviton, right? So what is nice also is that you can check the validity of this expansion by comparing again this term to this term, and you can check that this expansion is okay for R now much smaller than the Weinstein scale. This is exactly the same scale which arises here, which is the same Weinstein scale as above, right? Okay, so so soon after Weinstein paper in 1972 as well, after this paper of Einstein, there was a paper of Boulware and Deser that I already mentioned several times, I guess, which attacked this idea of Einstein in several ways. But one thing they pointed out is that there was no proof, of course, that this expansion and the other one would join together in some existing solution of the theory, right? Which is of course, a correct question. And this question of joining together the solution was left unanswered for a very long time. And in fact, it came back to life after the DGP model, because in the DGP model, there is massive gravity. In a sense, now it's more complicated than the theory we have here, but gravity is mediated, as I said, by a resonance of massive gravitons. So you have a VD-VZ discontinuity for all these massive gravitons. And what was discovered in this model was, if you look at the cosmology of this model, so is the equation I gave in section 1.3, well, you find that the cosmology is interpolating between solutions of ordinary general relativity, right? So h square plus k over s square is 8 pi g Newton rho with the g Newton of the action, where there is no renormalization of the Newton Newton constant, etc., as you could have expected because of the discontinuity, right? So the cosmology of DGP is interpolating between this and another behavior at large distances, right? For as I said previously. So this was a sort of a hint for a working Weinstein mechanism, that is to say a recovery, a non-perturbative recovery of solution of general relativity in a solution with massive gravity. That we pointed out with Giad-Vali, Gregory Kabadadze, and Arkady Weinstein, in fact, in 2002. And then I believe the first proof that it worked as Weinstein predicted in a theory of massive gravity like the one I presented so far, and it was provided by my group with Evgeny Babitchev, myself and my student of the time, Riyad Ziour, in 2009-2010. What we obtain is we obtain numerical solution of the equation I raised in the framework of spherical symmetry and static case, showing that there is, in fact, a solution which interpolates, right? That there is an existing solution. Even though this Weinstein mechanism has been used since this DGP ID and before us in a variety of setup, including Galileans, etc., as a way to, get rid of the unwanted effect of an extra scalar polarization here, or scalar field, the one which causes the Van Mellman-Sakharov discontinuity in cosmology. How much time do I have? 10 minutes? Plus question. Yeah, so okay, it will be difficult. So I would like to now to turn to another aspect of the Boulware-Deser criticisms, which was also very important, which is the so-called Boulware-Deser ghost. So in the same paper, they pointed out another pathology of nonlinear completion of massive gravity due to the following fact. So recall that in the previous lectures, I expanded the mass term of Pierce-Pauli in using a space and and time and space split. And so there was, I pointed out, there was a special form for the H0 piece, which was that H0 only appeared linearly right into this mass term. And there were then other terms, right, plus Hij, etc. Okay. So now there is minus sign here, I guess. So now the issue is these variables, these H, are not suitable variable to discuss Hamiltonian decomposition of a nonlinear theory. What you should use instead is the lapse and the shift. The lapse and as defined in the usual way, and the shift. For the special part, you can stay with Hij, right? Because this is just, I mean, you can just shift the metric by eta Hij, and this is okay. But now, if you use these variables, in fact, this is replaced by 1 minus n square plus nk gkl nl. So what was linear into H0, when you use a suitable variable to analyze the kinetic term now, it's no longer linear. It's become quadratic. So it means you lost the constraints that you had due to the linearity of H0, right? Because now it's become quadratic into n, and hence instead of having in the as in the linear theory, instead of having 5 degrees of freedom, you have 6 degrees of freedom now, because you lost the constraint which eliminated the 6 degrees of freedom previously. And you can also show, as Boulware and Deser did, that generically the Hamiltonian will be unbounded below. So this 6 degrees of freedom, this new degree of freedom that appear at the nonlinear level is called the Boulware-Deser ghost. Because, so it's a new degree of freedom, and it's a ghost because generically you can expect the Lagrangian, the Hamiltonian to be unbounded below. Okay, so I guess I have 5 minutes, something like that. Tell me. Yeah, but there is some festivity, no? So I have to finish on time. 15? 15. Ah, so that's okay. Okay, so the presence of this ghost was an obstacle for a very long time to consider any massive gravity, any nonlinear massive gravity theory, because it was thought to be unavoidable. And it's only recently that it was understood that it's not the case, and that Boulware-Deser were wrong. And to do that, to discover this theory, people use the following trick that I'm going to explain in the last 15 minutes, which is called the decoupling limit, which is a very interesting way to analyze this theory, which was proposed by Arcani, Ahmed, Georgi, and Schwartz in the paper I mentioned previously. And so the idea is to basically use a Stuckelberg trick to reintroduce gauge invariance in the game. So imagine you start from some coordinate system where the metric have a specific form. You can go to another coordinate system where the dynamic Krohn metric is g mu nu is equal to d mu xa, d nu xb, gab, but you go to a new coordinate system, so you forget about this old coordinate system. But for the metric f, let's say you keep the old form explicit. So it means you just keep the change of coordinate in the action. So this you consider now this as your metric in the action. And so instead of having a metric, you see you can consider you have in fact scalar fields, because this xa under a coordinate change they would behave as scalar field. So you have a theory now with one dynamical metric, which is g mu nu, in coordinate x mu, and for scalar field xa of x. And And you have gauge invariance because you can now change x to new coordinate, right? And then you have a gauge invariance. So this is analogous, if you want, to what you can do if you consider the Proca mass term for a vector, right? So this Proca mass term, it is breaking explicitly gauge invariance, but you can reintroduce gauge invariance by setting that A mu is a new field A tilde plus a scalar field, and then you have now a gauge symmetry, which is the usual one for A tilde, and where phi then shift in this way. Okay, so this is the same trick that you do here. And then the idea is to expand. So people use the same terminology for that reason, and in particular, they call, one can call the situation where the XA are trivial. So there is a gauge where XA is just trivial, right? You can call this the unitary gauge, in analogy to gauge, to standard vector theory, say. And then you can expand around this unitary gauge the theory. So you write, so let's call this XA0. So you write XA is XA0 plus some pion field, if you want, pi A of x. And the idea is that this pi A of x will encode the extrapolarization of the graviton, the 3 extrapolarization of the graviton, in an analogous way as here. You can say that this phi will encode the scalar polarization that a massive vector has in addition to a massless vector. So since I think I don't have much time, I will not give the detail of this procedure, but I will give the result. And there is an interesting story behind, but I don't think I have time to explain it. 10 minutes? So maybe I have some time to explain it. Okay, so if you follow this decomposition, first you can write your pions as in the following way. So you introduce a vector and also a scalar in the same way as I introduced for the case of the Proca field, because then you have also a gauge invariance in the vector sector. Okay, and then you insert everything into the action, and you expand everything at quadratic order. So the mass term, so this is the mass term, the Fierz-Pauli mass term, and what I'm saying here is generic for any nonlinear Fierz-Pauli theory, because I'm going only to write term at quadratic order, and at quadratic order, all these theories have the same form. So this mass term, so it's let's say I consider only the Lagrangian, so it's proportional to the following thing. I have the Fierz-Pauli form, where, yeah, I forgot to tell you that I also expand, of course, the dynamical metric. So I also write that G mu nu is eta mu nu plus H mu nu. So this is this first term here. And then I have terms which arise from this expansion here. So I have a first kinetic term for the vector. And this is similar to what's happening in the Proca case, because in the Proca case, right? So if you just basically consider this and then the mass term of Proca, you get a kinetic term for phi, right? So this term is analogous. But then there is a difference for the scalar sector. So you have some coupling between the vector and the scalar. And the phi field here, and this is the difference with Proca, it doesn't have a kinetic term beyond mixing. So it has a mixing with H. And that's all. So there is no d mu phi, right? So you only have a mixing. So you can demix this guy by by just defining a new h as being an h hat, say, minus m square eta mu nu phi. And I think there is a missing m square somewhere. No, maybe not. Okay. You can demix this in this way, and if you do that, then you built a kinetic term for phi. So in this new variable, now the mass term would read. So there will be still the Fierce-Pauli mass term with the kinetic field, the kinetic term of the vector. Then there is still this mixing here with the vector and the spin 2. And then you have a kinetic term for the scalar. Okay, whatever. And in addition, you see this, because in this original theory, H, the only thing which couples to the energy momentum tensor is H mu nu, right? Because the coupling only comes from the coupling to the metric G, which contains H mu nu, while F, which the other metric, from which this comes from, is not coupled to the matter. But because of this demixing, now you have a coupling between the energy momentum tensor and the scalar. So you have a phi t term that appear, and this is from this that you can read the existence of this Van Damme-Sakharov discontinuity, because basically phi in this language is parametrizing the scalar polarization of the graviton. So it is coupled to the trace of the energy momentum tensor, and it is this guy which exerts this extra attraction. Okay. Then the next step is to canonically normalize the field. So for that you have to rescale the field, because in particular you see here there is an m square in front of the kinetic term of phi, which is not present in front of the vector, for example. So you can do this rescaling and look at interactions. That was only for the free theory. This is a quadratic action. But if you look at interaction, you can discover that these guys interact together. This polarization of the graviton, H mu nu here, which is the two polarization, the two tensor, the two vector, and the scalar, they interact together in a specific way, which then now depend on the theory you consider. Because so far I only wrote the the free part, but which agree for all this theory in this nonlinear Fierce-Pauli class. But the theory I presented before will differ at the cubic order and then at higher order. Okay, so examining the let's call phi tilde A tilde mu, say, and H tilde mu nu the canonically normalized field. And if you classify the interaction at cubic order, you find that there is, in particular, at cubic order, for a generic theory, nonlinear Fierce-Pauli theory, there is a cubic interaction of phi tilde with itself that is suppressed by a specific scale. Suppressed by a specific scale, which is called usually lambda 5, and which is just m to the 4, m Planck to the power 1/5. And this is a strongest scale among the interaction. So in particular, you can take a limit, which is called the decoupling limit. When you let m Planck goes to infinity, m goes to 0, you fix the scale lambda 5, and you fix also the coupling to matter. So this is fixed, eh? in this limit. So this is so-called decoupling limit. And in this limit, basically the h tilde mu nu and the h tilde mu becomes free. They don't interact together. They are just quadratic action. You don't have any mass term for the graviton anymore, but you are left with only this self-interaction of phi tilde. So you get a very simple theory if you just look at the scalar sector, which has this following action, d for x. Then there is a phi tilde box phi tilde. It's the kinetic term of phi tilde. And then there is this self-interaction to the power 5 here. Okay. And since I'm really close to the end, maybe I will not give the detail of this self-interaction, but just it has the structure of box phi tilde to the cube with some number depending on the action, and there is a similar term with two derivatives with different tensor structure. And then there is a coupling to the trace of the energy momentum tensor suppressed by 1 over m Planck. So I'm almost done. I wanted to say that out of this decoupling limit, in fact, you can read many of the crucial properties of nonlinear massive gravity. You can read the Van Damme-Sakharov discontinuity by the presence of this guy coupled in a m-independent way to T. You can read the Weinstein mechanism as being due to this self-interaction, in fact. You can really show that the Weinstein mechanism is due to the existence of this interaction which kicks in at very large distances. And you can read also, in fact, the presence of self-accelerated solution, etc. I have to stop. Okay, so just to stop here, let me say just a few more sentences on this is what's happening for generic nonlinear Fierz-Pauli, but it is not what is happening for the theory of de Rham and Gabadadze-Tollé. For de Rham, Gabadadze-Tollé, and this is in fact how they found their theory, because I didn't say that also, but here you can also read the presence of the Boulware-Desert ghost from this action, from the fact that the equation of motion of this theory has higher derivative. In de Rham-Gabadadze-Tollé, you have a different interaction and a different scale, which is larger, which is m square, m Planck to the power 1/3. And you don't have such a term, you have a different structure which doesn't yield a higher derivative. And this is how they discover their theory. So the claim is that the de Rham-Gabadadze-Tollé theory is devoid of the Boulware-Desert ghost. And this is the first theory of this type. And one can show the only one, in fact, which doesn't have this Boulware-Desert ghost. So, yeah, it's due to the. So for any of these coefficients, it works. But what is specific is a form with this square root and this, symmetric function. So, and this is a big discovery of de Rham-Gabadadze-Tollé. And since then, it has been used in various ways. And I don't have time to discuss all this extension. There is a whole literature on that, very interesting. I don't have time to do that. But this started a lot of interesting work. And if you're interested, I just would like to mention reviews. So there is a review of Kurt Interbichler on this subject of 2011. And there is also a living review of Claudia de Rham, where in particular aspect of this de Rham-Gabadadze-Tollé theory is discussed. Right. So I think I have to stop because otherwise Roland will get mad. Yes, well, yeah, so I didn't have, maybe there is no advantages. But, and I don't know, I don't have much time to discuss that, but people have used this, the idea, as I said at the beginning, one of the ideas is to use this to do cosmology, so to replace cosmological constants or dark energy by this modification. So it doesn't work so well, in fact, even though there is one nice aspect which is present in this theory, which is that there is a technical naturalness of having a small graviton mass because of the fact that when you let m goes to 0, you recover symmetry, right? You recover Diffeo invariance. So maybe, you know, this is interesting for that reason, that in contrast to just having a standard cosmological constant, here you have something which protects the smallness of M. But this has been used now to a lot of things, and I don't have time, right? Okay. Yeah, so yeah, I can answer to question later on, after the concert.
Tu t'en vas pas? Non, non, je m'en vais pas. Il y a...
Je démarre, c'est ça?
Tu démarres, tu dis qu'il va avoir...
Je vais voir quoi?
La cantatrice après.
Ah oui. Ah, c'est moi qui vais le dire? C'est toi qui vas le dire. La cantatrice.
Ah, c'est tout. Oui. Non, c'è forse.
Meglio fare questo quando avete finito.
Mario. Mais alors il faut qu'elle me laisse le truc là.
Ceci, voilà.
C'est minutes, hein?
Não, aqui em cima não. Já...
Outra mesa? Quer que eu bote outra mesa ali um pouquinho?
Talvez seja bom. Primeiro você...
Vou primeiro pegar a mesa.
Bota a mesa aqui, é. Aconteceu? Martin, parce qu'il faut enlever ça. Flávio, você pode pedir alguém para tirar isso aqui daqui? O cara foi buscar uma... Não, você é pesado.
Il marche? Yes. Ah ouais. D'accord. Ah, c'est lequel? À droite, à gauche? Ah, c'est ça. Non, ça marche pas.
L'autre.
Ah, d'accord. Ça? Non, ça c'est le truc.
Oui, mais l'autre, elle change la page.
C'est laquelle? Celui-là en bas ou
oui.
celui-là? En bas. Et pour remonter, c'est celle-là. D'accord, ok, très bien.
que c'est isso? J'attends un moment? D'accord. Mais qui reste là pour qu'il rentre. D'accord. Ok. Microphone. Tu veux le micro? Tiens, tu veux le micro? Tu veux ce micro-là? Donne. Je le fais. Je le fais. Tiens, tu veux ça? Tu veux ça?
Funcionando, João? Ok. Boa noite a todos. Nós vamos aqui agora começar uma sessão um pouco diferente. I will speak in Portuguese, but later on I will translate in English. We just start this celebration of the 40 years. We shall see that there are other people coming, but we cannot wait because it's too late. And we have the pleasure to talk with the Minister of Science and Technology, Alberto, which is here, which is one of the men responsible for the success of this school. And let us wait that other peoples will come. And I ask to start all this to Professor Roberto Moral to speak some words to our commemoration.
Quero fazer, boa noite, vários pedidos de desculpa. O primeiro pelo paletó, mas aqui Quando eu saí, estava meio frio em Laranjeiras. Então, eu pensei que na volta estaria mais frio. O segundo é que vou falar em português. E terceiro, aliás, são 4. O terceiro pedido de desculpa é que eu vou ler. Né? Eu fiquei com muito medo da plateia. Né? Aí, tipo, tentar fazer de improviso, ou de meio improviso. Isso é perigoso, então eu fiz escrito. Mas o Mário tinha me dito que eu trabalhasse com algo como 15 minutos. Quando eu terminei, hoje, muito cansado, certas coisas cansam, eu vi que eu fiz um teste, dava 20 minutos. Eu fiquei assustadíssimo, né? O que eu vou fazer com esses 5 minutos excedentes? Pensei em cortar, mas esses cortes de última hora são difíceis, principalmente a gente cortar os textos da gente. Dos outros é muito fácil. Toda hora que eu olhava aquele texto eu gostava, e desisti de cortar. E vou pedir desculpa, vou falar uns 20 minutos. Como a minha dicção é péssima, se eu ler correndo, aí que ninguém entende mesmo. Então eu vou pedir desculpa para ler um pouco lento. E, afinal, eu vou agradecer algumas ausências, se isso é possível, da indelicadeza, porque me permitiram mais tempo. O meu excesso de tempo não vai ser notado. Eu posso falar de 20 minutos. Eu proponho uma discussão, uma reflexão em torno da díade ciência e ética. Como vocês sabem, a minha formação não é de físico, nem estou ligado a nenhuma das matemáticas. Eu sou das chamadas humanas. Não é que a física seja desumana, mas a universidade chama as humanas. Então, eu sou das humanas, que não sabem nada de matemática. Imaginando uma tábua de valores específicos, isto é, próprios da ciência, convido-os a discutir a responsabilidade moral e ética do cientista em face das consequências da aplicação de suas descobertas, de seus inventos, ou seja, do saber gerado. Esse cientista não é um extraterrestre, mas um ser político, integrado em determinada sociedade, um produto histórico com passado, presente e inquietações quanto ao futuro. O pano de fundo é este. Somos passageiros da mesma nave, numa grande aventura pelo desconhecido. Convivem conosco, no mesmo experimento, o mundo da pesquisa científica, acadêmica ou não, pura ou não, com seus valores próprios, e o mundo da ordem política, também com seus valores próprios, onde a teoria se transforma em prática, em objeto concreto, saltando dos laboratórios para o nosso cotidiano, alterando o mundo. Trata-se, pois, de universos autocomunicantes, interdependentes como irmãos siameses, todos condicionados pelas circunstâncias históricas, as mesmas que ditam os parâmetros axiológicos. Há uma ética própria do cientista convivendo e dialogando com uma outra ética, distinta, a de quem financia a pesquisa, seja o Estado, a serviço da paz ou da guerra, democrático ou autocrático, seja a indústria, voltada para o lucro e a acumulação capitalista. A ciência é história e filosofia. Filosofia porque, sendo ação humana, responde a um quadro de valores. História, como assinala Mário Novello, quando consideramos a dependência cósmica das leis físicas, sua variação com o tempo global. Ao verificarmos essa dependência das leis, reconhecemos a historicidade da cosmologia. E como sua função é refundar a ciência, evidencia-se claramente seu caráter histórico. A ciência, portanto, deixa de ser um valor em si, autônomo, ahistórico, autojustificado, ofício dos deuses de um Olimpo inalcançável, valorada que é pelo papel que desempenha na experiência humana. A ciência é, fundamentalmente, um produto social, e o cientista é, de igual, produto de seu tempo e agente de transformação. É, nestes termos, responsável pelo que faz ou deixa de fazer em proveito da sociedade. O cientista, como todo intelectual, é um ser político, certamente ainda mais responsável do que o comum dos homens, ou o comum dos políticos, em face de sua formação privilegiada, geralmente custeada pela sociedade e pelos impactos provocados por seu trabalho. Então pergunto, a serviço de qual fim está a comunidade científica brasileira, ensurdecedoramente silente, quando vivemos aquela que é, por certo, a mais grave crise da história republicana, pois compreende o colapso do Estado, a desintegração das instituições, a destruição de nosso patrimônio, a recessão e o desemprego e a renúncia ao desenvolvimento. Nada temos a dizer quando se depara diante de nós, é uma pergunta, nada temos a dizer quando se depara diante de nós o desmantelamento da educação, da ciência e da tecnologia? Quando nossas empresas, nada temos a dizer quando nossas empresas são vendidas na bacia das almas? Quando está em jogo o futuro da universidade pública, ou seja, o futuro da pesquisa científica e a democratização do ensino e do saber? O protesto e a rebeldia, tanto quanto a acomodação e o silêncio, definindo condutas, define o papel do homem na história. Ou seja, o papel que o homem do povo, o cientista, o político, o filósofo, escolheu para desempenhar. O homem se escolhe, mesmo no seu laboratório. A dedicação dos cientistas construtores da bomba atômica norte-americana está eticamente apartada, é uma pergunta, está eticamente apartada da decisão e responsabilidade do presidente Truman de jogá-la contra as populações de Nagasaki e Hiroshima? Porque o cientista escolhe consagrar seu conhecimento e sua vida à pesquisa de uma fórmula ou de uma inovação que poderá ser responsável pela morte, pelo sofrimento e pela destruição de seus semelhantes? Por que não utilizar sua liberdade de opção para impedir o genocídio, para atenuar o sofrimento, para melhorar a qualidade de vida, se sempre é possível escolher, como demonstram os cientistas que se opuseram ao armamentismo do Terceiro Reich? Nessa Alemanha do Terceiro Reich, muitos cientistas aderiram ao Manifesto de Fulda, em apoio à visão política de que a ciência alemã devia estar a serviço irrestrito da pátria e dos alemães, ou seja, do genocídio. Mas Einstein e alguns poucos colegas se recusaram a assiná-lo. Outros intentaram mesmo sabotar o esforço nazista, como, entre outros, Werner Heisenberg. O cientista não está condenado a renunciar aos seus valores. Há sempre a liberdade de opção, e assim, todos se tornaram igualmente responsáveis por suas escolhas. Uns pelo desenvolvimento científico da Alemanha do Terceiro Reich, outros pela sua denúncia, pelo seu enfrentamento, agindo pelo silêncio ou pela omissão. Alguns abandonaram o esforço alemão para contribuir com os Estados Unidos ou com a União Soviética na corrida pelo domínio da fissão nuclear, numa guerra que seria vencida por diversos fatores, dentre todos se sobressaindo a ciência e a tecnologia. O cientista, como filósofo, como qualquer intelectual, é, independentemente de sua escolha, um ser eticamente comprometido com o progresso humano. É, portanto, um ser responsável, porque é, antes de tudo, um ser livre para optar pela sua linha de pesquisa. É ator responsável pelo papel que desempenha, porque é ele mesmo quem escreve o seu script. A construção do Terceiro Reich, lembremos-nos, não foi obra exclusiva de políticos, militares e empresários. Resultou da dedicação e competência da comunidade científica, de filósofos e de juristas, como Heidegger, Smith, Lorenz e Huber. Valho-me do paradigma alemão, consensualmente aceito, mas sabemos que o espírito de Fulda permeia a história da humanidade e está presente em nossos dias na política dos países dominantes, cujo esforço de guerra baseia-se no desenvolvimento científico e tecnológico. Nós já ouvimos falar aí, ao invés de Heil Hitler, American First. Qual seria, ou qual deve ser, a ética aplicada à pesquisa científica, se não aquela que a destina à preservação da vida e ao bem-estar da humanidade? Neste caso, admitindo-se uma axiologia específica para a ciência, a que princípio ético estaria subsumido o pesquisador que trabalha conscientemente na fissão nuclear voltada para a bomba atômica ou na pesquisa de artefatos militares de destruição? Poderiam ter ilusões os que ontem trabalhavam em Los Álamos, os que hoje trabalham na guerra química e bacteriológica ou cibernética? Como valorar a ciência voltada para a guerra e o extermínio massivo? Nos países do chamado Primeiro Mundo, 80% dos fundos para a pesquisa estão hoje diretamente relacionados às necessidades da indústria da defesa, que, na verdade, é a indústria da guerra e da agressão. Muitos pensadores estão persuadidos de que o avanço da humanidade, em particular o progresso científico e tecnológico, se dá mais aceleradamente nos tempos de guerra. Mas é durante a paz que se prepara a guerra. A corrida armamentista ocorre nos intervalos dos grandes confrontos, para atender a imperativos do desenvolvimento do complexo militar industrial. Se alguém quisesse me socorrer com um pouco d'água, agradeceria. O fim da guerra decorreria do fim da disputa por mercados, o que seja um paradoxo, pois seria, igualmente, o fim do capitalismo, que tanto impulsionou a ciência. Robert Oppenheimer, um dos inventores da bomba atômica, que com von Braun trabalhou dos dois lados da fronteira, tornou-se símbolo da alienação em que, como mecanismo de defesa, mergulham os cientistas quando os interesses de um Estado colidem frontalmente com valores humanistas. Perguntado como teria sido possível contribuir para a construção das primeiras bombas nucleares, Oppenheimer, conhecendo como conhecia a destruição que necessariamente causariam, teria respondido mais ou menos assim: preso às quatro paredes do meu laboratório, eu estava de tal forma polarizado com a busca triunfante dos resultados que em nenhum momento dei-me conta de suas consequências. Evidentemente, nenhum de nós aceita essa explicação, mas isto ilustra o fato de que o cientista, ao contrário do tecnologista, quase sempre este dominado pela descoberta em si mesma, está muito mais preocupado com a elegância da equação que traduz um novo princípio do que com aquelas consequências que isto possa provocar na prática. Um bom número de físicos respeitáveis, entre os quais o Nobel Steven Weinberg, insiste em dizer que a ciência, e particularmente a física, para nada necessitam da filosofia, limitando o seu trabalho ao manejo adequado do método e ao domínio pleno das matemáticas que lhes serve de linhagem. Esta posição não resiste ao exame dos fatos. É, por exemplo, o que se deduz do desenvolvimento da história recente da ciência, bastando lembrar os desdobramentos da teoria quântica. Os resultados até aqui obtidos, da teoria quântica e outros, obrigaram os cientistas a rever os mais sedimentados conceitos da física, desde o determinismo newtoniano e a causalidade de Einstein, consagrando em seu lugar o indeterminismo e a ação à distância, na ausência de um meio que fizesse ligação entre causa e efeito. Apesar de continuar, não só regras, princípios, apesar de contrariar, não só regras, princípios e conceitos bem estabelecidos, e desafiar o senso comum, a teoria quântica tem a seu favor o fato de que postulados seus estão se transformando em aplicações de que a humanidade se vem beneficiando. Esta aparente contradição entre a realidade e a verdade científica tornou necessária a elaboração de tentativas de compreensão dos fatos, um exercício de análise a que se convencionou chamar de interpretações da mecânica quântica. Todas elas face ao desafio de descrever o fato e de descrever o que de fato é a realidade. E de todas elas, seja a interpretação de Born e Heisenberg, a chamada interpretação de Copenhague, que parte do pressuposto segundo o qual uma partícula não existe até que seja observada, o que nos leva de volta a Platão, seja a interpretação de David Bohm, que postula a existência de mundos paralelos, e todas elas, e tantas outras, não passam de construções filosóficas. O universo não é em si, não é ele em si, mas como a ciência, o universo não é ele em si, mas como a ciência nos leva a conhecê-lo. E esse conhecimento varia a cada dia, de sorte que o universo de hoje é tão distinto do universo de nossos antepassados como distante do universo que resultará do conhecimento futuro. Como sugere ainda Mário Novello, o universo está em permanente invenção, ensinando-nos que todas as certezas são provisórias. A verdade científica é pro tempore. Reina até a próxima descoberta, que quase sempre já vem a caminho para superá-la. Platão, Euclides, Aristóteles, Ptolomeu, Copérnico, Galileu, Euclides, Newton, Einstein. Eu pensei em colocar aqui o Bruno, mas fiquei receoso se cabia ou não. Bruno, seu compatrício. Em nome de supostas certezas e verdades passageiras, quase sempre de fundo religioso, quantos crimes foram cometidos, quanto atraso foi imposto à marcha da civilização. A ciência é possuidora de uma história própria, ou, o que praticamente dá no mesmo, é a de histórica? Já sabemos que não. O conhecimento singulariza o ser humano entre todas as manifestações de vida em nosso planeta. Porque foi conhecimento a conquista do trabalho, o esforço contínuo do homem, desde os seus primórdios, para transformar a natureza, dominando-a em seu benefício, até delegar-nos o mundo de hoje. O avanço do conhecimento, como o avanço do poder, todavia, jamais foi simétrico. Quaisquer que tenham sido as razões dessa disfunção, e me inclino para as explicações históricas, o fato evidente é que o homem conquistou a terra brandindo um apetite insaciável pelo domínio dos bens naturais e sua apropriação pela posse, e como corolário, pelo poder, mesmo quando de seu preço constava o sofrimento, a marginalização e o próprio sacrifício, a dor e o sofrimento de seus semelhantes. O império da lei foi sempre da lei do mais forte, a razão do mais forte, o diálogo do lobo com o cordeiro, cuja razão e lógica foram imortalizadas por La Fontaine. Mas, simultaneamente, a humanidade, no seu processo de autoconservação, foi tecendo regras de convivência indispensáveis à própria sobrevivência, condicionando-as como ética, a norma maior, vértice de seu desenvolvimento, justificativa a condenação dos atos do ser humano, cumprindo com seu papel de construtor do mundo. Está no final. De outra parte, não há associação entre democracia, essa que conhecemos, e avanços éticos ou progresso científico. A derrota dos regimes autocráticos é a adoção majoritária de regimes fundados no modelo ocidental de democracia representativa. Conquista da burguesia do terceiro estado não tem significado maior avanço ético. Proliferam a fome, as guerras, proliferam os desterros, as diásporas, o genocídio. As vitórias da ciência, seu desenvolvimento nos últimos anos, não construíram a paz. Finda a Guerra Fria, após 2 guerras mundiais, a primeira alimentada pelos avanços da química, a segunda coroada com o cogumelo atômico, explodiram pelo mundo inteiro os conflitos de toda a natureza. A insânia, todavia, tem sua lógica e sua razão de ser, porque a guerra é fundamental para a alimentação da indústria moderna, que abarca quase todos os ramos do conhecimento científico. Seu preço tem sido o aumento da pobreza e do número de desabrigados, construindo levas e levas de desesperados apátridas. Os financiadores da ciência, que vasculham o espaço sideral e constroem escudos de mísseis estratégicos, não cogitam da miséria da África, se esvaindo em diásporas, porque o desenvolvimento que suscita se destina a manter o domínio sobre os povos. Os fomentadores da ciência, que se apetrecha para a exploração de embriões e clones humanos, não voltam seus recursos para enfrentar o empobrecimento do mundo. Graças às novas tecnologias, no entanto, e eis outro paradoxo, é cada vez mais restrito o livre acesso à informação e a disseminação do conhecimento cede lugar à proteção intelectual. Há justificativa para o fato de nossa formação científica ignorar a disciplina de introdução à filosofia? Ignorar o estudo das humanidades? Estas questões são científicas e assim se bastam, se resolvem ou cobram a ética reguladora da conduta científica. Que se deve entender relativamente à ciência por princípios éticos? Sua aplicação democrática, e por democrática podemos entender o universal? O cientista, antes de tudo, um cidadão, deve comprometer-se com o combate à fome e à exclusão, a começar pela exclusão do conhecimento. Cumpre-lhe, qualquer que seja sua área de atuação, defender o direito à saúde, à educação, à moradia e à terra. Cumpre-lhe estar à testa do combate à intolerância, à discriminação e à guerra. Quais as consequências impostas? É outra pergunta. Quais as consequências impostas à nossa conduta pela consciência de que nossa formação científica e nossas pesquisas são financiadas por um povo que não teve e cujos filhos não terão acesso à universidade e ao conhecimento, ao conforto e ao bem-estar, muitos mesmo sem acesso à vida digna, à cidadania e ao direito de alimentar-se? O cientista intervém na realidade tanto quanto o político. E o intelectual marxiano é o intelectual marxiano, das teses sobre Feuerbach. Seu destino é igualmente transformar o mundo. Cabe-lhe decidir por qual mundo lutar. Porque não lutar é também uma maneira de optar, de tomar partido pelo atraso. Obrigado.
Obrigado, professor Ministro Roberto Amaral. I will talk now Roland Trier pour pour parler sur.
So in order to prevent for a long discussion, I prefer actually to read. Everybody knows, but they can take longer. So the 17th Brazilian School of Cosmology and Gravitation is dedicated to the memory of Professor Edgar Elbaz, who sadly passed away on January 13, 2018, during his 82nd year. So Edgar, professeur honoraire de l'Université de Lyon, officier des Palmes académiques, officier d'ordre national du mérite, chevalier des Palmes académiques polonaises. If you met him at the airport waiting for your plane because of delay, you meet him, you discuss with him, you never guess who he is. Because this man was a very modest man. So I would like to introduce you this person. So Edgar was an active member of the scientific organizing committee of the school from 1993 to 2017. This is the reason why we wish to dedicate this year's school to pay a tribute to him. To the question, that you could ask what kind of type of man it is, you will discover when I will present this introduction. Non. Comment ça marche? Ah, ici, okay. So, Director of Science in 73, thanks to this work, he received a Jean Thibault Award in 1967. He's appointed professor of theoretical physics at 34 years old, and he quickly became vice president of the University of Claude Bernard of Lyon from 1976 to 1980. He took the direction of the Institute of Physics Nuclear Physics of Lyon in the 82 until 88. And as well as the university, well, it is actually associated to university and the CNRS. And it is an institute of 200 people. It provides to the IPNL, this is the acronym of the institute, with a rigorous structuring of which many elements still remain at the moment. The major scientific event that had taken place under his leadership, which would often be decisive for its long-term orientation of the IPNL. Among those Well, actually, it was his main ambition for this institute. For example, the Sarah project, which large defined subsequent in the field of nuclear structure of heavy ions. The L3 collaboration in research of the Higgs bosons. Another one, which led to the creation of the mirror for the detection of gravitational waves. And the one at CERN for the detection and study of a quark and gluon plasma. So it was during this period, in 1986, that Edgar took over the 10 years of the Institute of the Science of Matter, before becoming, from 1995 to 2003, vice president of the university in charge of international relationship, were particularly important to him. He had also served for 8 years on the board of the directors of the International Association of the University, which is actually a structure which covers all over the world and in charge of the education and so on. So actually, it took a quite interesting place in Erasmus project. No, yes. So his domain of research, it is actually a very brief introduction of him. In domain, so he began a career as a researcher in theoretical physics, then in quantum mechanics and particle physics, and finally in cosmology. He has published hundreds of articles in peer-reviewed specialized journal and several scientific books. Actually, this kind of book was a consequence of his research. Traitement graphique de l'algèbre de moments angulaires, it's 69. So it is actually French. So at that time, I am witnesses of the translation, of the transition between scientific people in French, writing in French, and having difficulty in speaking English as well. The French actually was very well protected. Actually, the last topics has changed, moved into English was mathematics. So graphical, so it was very well known in this particular field. And actually, it's a translation of this book, Graphical Method for Spin Algebra, in Marcel Decker, etc., and Mir as well, in Russian, was published. Interaction fondamentale et structure de la matière, algèbre de Urca et analyse graphique, in ellipse, de l'électromagnétisme à électrofaible, quantique pour un profane. So this kind, so actually he wanted to promote science among his physics colleague as well. No, ici, yes, no. So about course, when you're a professor at a university, you have to challenge research and lecture as well as everywhere. But in France, particularly, actually, we have a huge amount of teaching to do. So it took from 1962 to 2005 several courses such as optics, mechanics, quantum mechanics, general relativity, and cosmology, and published most of them in textbook. These are the textbook and written as well in French, the title, and except one, Quantique. It has been translated in English and in Polish as well. It was very well known, actually, because of this activity all over the world. Yes. Promotion of physics. So he promotes science, knowledge, and training for young scientists. And he was the first director and founder in the 1968 of the University of Scientific Evenings in Villeurbanne, an area surrounding Lyon, where I live. In 1993, and the Open University. Actually, the Open University was a possibility to children and parents to meet in the university to make experiments. And actually, these two, in particular, these two initiatives that continue to be very successful today, nowadays. He was also at the origin in 1972 of the seminar of nuclear physics of La Toissure, in which he was a director for 10 years, and of the seminar Transempent Physics from 1990 to 2005. So, merci Edgar, actually. We can say. The scientific organizing committee of the Brazilian School of Cosmology and Gravitation will miss Edgar Elbaz as a colleague and friend.
Thank you, Roland.
Okay.
Just to end this ceremony, before we enter to this song part.
D'émotion. J'ai un peu d'émotion.
Comment on fait ça?
Bon. Je le fais.
Non, c'est pas nécessaire. Je fais ça. Okay, so I'll read in Portuguese, but you can see in English. Mas eu preciso dos óculos. Durante as BSCG, nós contamos com o apoio de personalidades que ocupavam importantes cargos na administração ligados às atividades científicas, como nosso ministro Roberto Amaral, diretor científico da FAPERJ, Gerson Lima da Silva, o ministro Sérgio Rezende, diversos presidentes da FINEP, simbolizados na figura de Luiz Fernandes e Vanderlei de Souza, que foram convidados para essa cerimônia, mas por estarem envolvidos em Brasília a busca de recursos para nós, não puderam estar aqui hoje. Agradeço a Glaucia Pessoa e sua equipe, Ampersand e Henrique Viviani, por esse belíssimo livreto que todos vocês receberão em seguida, que representa alguns comentários sobre esses 40 anos da BSCG. A ideia de associar a memória das últimas BSCG realizadas nos últimos 20 anos em Mangaratiba foi extremamente feliz, como você pode ver depois nessa belíssima foto de Mangaratiba. Aqueles que conheceram Mangaratiba reconheceram nessas fotos aquelas nossas atividades. Como disse um antigo aluno da BSCG, e depois ele se tornou professor em mais de uma edição da BSCG, ele diz que as BSCG prossigam por mais um tempo de Hubble, um pouco exagerado talvez, e que voltem ao formato típico das escolas de Les Houches, na Europa, e Aspen, nos Estados Unidos, onde, como a BSCG o fez durante mais de 20 anos, professores e alunos convivem durante o período do evento no mesmo hotel onde ela é realizada, tornando o contato científico entre os participantes mais produtivo. Infelizmente, as crises que estamos passando nos últimos anos e a atual praticamente impede que esse tipo de atividade continue ocorrendo. Esperemos que, com a mudança esperada do sistema ditatorial que a gente vive hoje, possa ser mudado isso. Agradeço às secretárias que nos auxiliaram muito nesses anos, em especial Flávia Schaller e Flávia, onde estão, como faz aqui para mexer isso aqui? Tá certo? A música que nós ouvimos e que vamos ouvir nos intervalos é da autoria de um jovem compositor, Luca Novello, que intitulou, por razões que só ele pode saber, Cosmos e Contexto. É essa música. Essa 17ª BSCG é dedicada à memória do professor Edgar Elbaz, que serviu durante mais de 20 anos como membro do Comitê Científico. Infelizmente não pôde participar. O livreto que estamos agora distribuindo não contém todas as informações da BSCG, pois os cursos ali dados já foram motivo de publicação nos 30 anos. E, finalmente, eu gostaria de agradecer ao atual comitê científico, formado pelos professores Kolbe, do Fermilab, Roland Trier, de Aix-Marseille Université, Dolgov, do Instituto Nacional de Física Nuclear, Baran Machum, da Universidade de Missouri e do Instituto de Astrofísica de Teherã, no Irã, Hugo Moschella, da Universidade em Subra, na Itália, assim como o comitê local, que foi extremamente importante nesses últimos momentos, os professores Sérgio Jorais e Martim Macra. Finalmente, aos professores que aqui estão, da 17ª BSCG, os agradecimentos em nome meu, da comissão e de todo o Instituto. Eu gostaria de terminar esse brevíssimo discurso com as palavras iniciais do nosso livreto, enfatizando que os argumentos que sustentam o modo padrão de descrever qualquer fenômeno físico não são suficientemente fortes para impedir uma análise distinta, baseada em hipóteses diferentes da versão oficial. Espero que as Brazilian School of Cosmology and Gravitation tenham conseguido realizar a tarefa de empreender o exame dessas alternativas. É do embate de ideias que a ciência progride. Em verdade, essa diversidade de ponto de vista, que às vezes parece ausente da prática científica, é que torna a nossa atividade importante e significativa. E eu só esperaria que essa dicotomia se espalhasse por toda a sociedade, permitindo a pluralidade de opiniões no dia a dia de nossas ações e o respeito pela opinião distinta dos outros. É o que deveríamos esperar ter em uma sociedade democrática. Muito obrigado a todos. Agora, eu pediria ao professor Hugo Moschella, que além de ser membro do comitê, além de ser um professor que dará seu curso amanhã, vai nos brindar com o nosso piano e com a nossa cantora, que desapareceu, parece. Onde? Roland, où est la cantatrice? Scusa? Sì, facciamo tutto questo, non c'è problema. Flávia, pode levantar isso aqui? Só um último comentário. Depois, então, vocês podem cada um pegar um desses livretos aqui em cima da mesa, ok?